I think it's your time. And after a I think you guys can
Okay, thank you for the generous introduction. Yeah, I know we are living in the technology advance freeze of society, but already right kind of this this is what people okay. Today I'm gonna talk about the title. As I said, the random finite set filters and their applications. Briefly speaking, what the random finite set means here is we want to we want to describe the world as a kind of objects. I want to call it as a set of objects, and also the we don't have a fixed number of objects, right? And then there's a randomness in the time, the number of objects, and then the state of the object itself. That's why we, as a random finite set, it means in the set there are two randomness here. First, the number of objects, and second, the state of the object. What I've been working so far is how to the two state of the finite set and the filters. The filter here means we want to reduce the uncertainty something and the applications. The applications I'm going to talk about classical tracking applications, including mosquito, lifestyle biology, and vision. And so outline of my talk today is as follows. First, I'm going to talk about what the state space model means. And if anyone familiar with theory, might have heard of state space model. Space model is a beginning to describe the objects as metaphor. And then I will move on to the definition of gentle definition of the ontology system by looking at some example out there. And then move on to the theory, then to the mathematical formulation of the object, and then filter that I need to try to reduce the uncertainty, the randomness of the system. And the theory consists of three parts mainly. First, the most of the states, and it could be the 2D location of the object, moving object, or it could be any states of the object, could be random variable. And as I said, the first one, and then there are two randomness. The first, number of objects, and then randomness in the state. And then after defining the modular system using the modular state and then random finite set, what we need to do in the real world is to reduce uncertainty. Because we are working on a stochastic system, so there needs to be some kind of intelligent algorithm to reduce the uncertainty. The application will be introduced. Okay, so I apologize. There's a little bit of mathematical equations, but not really that complicated. Just abstract level of mathematical. So if you look at here in the diagram, there exists the state vector here to the object. And then when we describe state space in 2D for the location of the object, we could model the movement of the object right here. Here, at the time k equals 1, there's a location in the state space, but at time k, the object might move forward, and we can describe it diagram here. The problem is, in general, in the ground truth is not known. Ground truth is only known in simulation. If you are working on the right, take this, somehow you need to validate by testing simulated data. The reason why we need to simulate data is because we need to obtain the ground truth so that we can measure some kind of distance between process data and the ground truth. Try to measure the error, right? But what I'm talking about here, this diagram, simple diagram is the ground truth not known, and then ground truth reveals only when we set the ground process state by using some sensors. So that's why in this diagram we are showing that the state is hidden, or somehow mathematically modeled. And the sensor system will look at this state by using some kind of sensors like a radar, vision, or LiDAR, anything. But when the sensor is looking at the object state, there is some noise here. So that's why I'm saying I draw the circle around the true state. And there's actually 30 bound of the sense. And that the star means that there's the sample data, the realization of the product distribution. Okay? So these two concepts can be mathematically described by using this simple application on the slide. What it says is that there could be noise in the state space, and then there could be noise in the observation space, and then because I'm considering the stochastic system, it could be described as a Markov density and a measurement likelihood function. This kind of general system. And this is just an example. Because the Gaussian is the simplest things, a very intuitive description of the system. What we are looking at here in this slide is that the uncertainty will be like this. The shape of the uncertainty of the system, to the object, location, and the sensor data. These are all described by a Gaussian shape distribution. And it has been investigated many ways. And in category of the research area, including signal processing and control and system application. So some of you are familiar with the control or signal processing or system application. This state space description is widely adopted in research. Right? So this slide just a summarization of the previous content from the. And then, let's assume that we describe the systems by using this slide and its location based on PDF. So what it means that the state will evolve in time using some sort of dimension density PDF, and these hidden states measured by the sensor, and then this uncertainty information is described by using likelihood PDF. Okay. And if you know two things, two types of PDFs, it means that you know the mathematical description of them. And what I'd like to do is try to reduce this uncertainty coming from state evolution time and the sensitivity. And in order to do that, there are many algorithms out there are many concepts out there, but myself and working on Bayes and filter theory. And Bayes and filter theory in discrete time as a model is provided by using these two steps. First, prediction step, and second, the data base. The first step on the left-hand side of the slide is nothing but propagation of the state. PDF of the state in the previous time came as one through the Markov density. And what you need to do is that you have to take integration with respect to the state of k-1. That's the integration version. And when you receive the measurements from us, you need to incorporate the measurement into the system. Algorithm. So the right-hand side, the lower side is Bayes rule. The simple Bayes rule. Simple Bayes rule means that you multiply the previous predicted city, predicted PDF by a measured likelihood function. And then you divide it by using normalized constant, is the base rule. Prior, likelihood, and normalized constant. Then so these two things are a very conceptual equation. And what the Bayesian filter does is that try to reconstruct two types of PDF in the prediction and of this possibilities. And just briefly, as I said, this is nothing new. It has been investigated in many decades, starting from 40s, and then outfits appeared around 50s and 60s, and it has evolved to various space applications and so on. Let me just take a short talk for anyone who's familiar with the common filter. If you know the common filter is some kind of core algorithm to estimate the state of the object, intrinsically the truth of the object by incorporating the measurement sense of data. So it has been applied in the Apollo program, and the common filter is running nowadays in the autonomous field. Any application related to time critical state estimation. Then the thing is that common filter is only useful for linear boundary system. And then so it has been extended further to accommodate nonlinear and non-Gaussian systems. So these two things are relatively recent. And then of course the common filter is one struggle for we want to extend it further for multiple systems. So what I'm here is my main research area, try to understand the multiple system, mathematical description, and after modeling, I want to develop an efficient mode of filtering algorithm to study the system. Okay, let me go back to again the slide. See the diagram, but it's extended further to accommodate all the uncertainties you can think of in the real applications. So, as I said, the pink circle is a certainty of the PDF, a PDF of the sensor, and a star is a realization of the data. Thing is, there's another type of uncertainties like the number of data, right? You are not only getting one data from it, you are getting many data from it. And then you don't know how many data you will get every single time step. And then it could be considered as a data loss or false alarm. Right? So these the diagram try to accommodate all the uncertainties like false alarm and data loss and the number of data. And the bottom here, and of course we want to extend the further to it for multiple system. And then at time came us on in this particular example, we have 5 objects. And in next time we might have 3 objects. It means 2 objects will die here from the essence of correct. Okay, so when we want to generalize the single system, we need to consider random number of objects and methods. And on top of that, the question uncertainty also allows, and this is association uncertainty. Right? So when you collect the data, of course, depending on the type of data, there will be some take, which means that this data is actually looking at this particular. But in general, we don't know the data is coming from which object. This is data association problem. So not only modeling all these uncertainties for object or the sensor data and so on, and we also need to solve the data association. That data is coming from this guy, or that data is from that guy. And well, there are many. If you are successful to model multiple system like this one, which is a very general concept, and you can apply like a defense application, surveillance, robotics, environmental, and so on. I will shortly introduce you to others. So this is just the brief example, like particle, molecules, cells, and then surveillance, autonomous safety. These are well-known examples of water resistance. So I just want you guys to try to connect the mathematical concept that I showed you earlier, space move, like state transition, magnetic function, and the random number measurement, random number object, and so on. How these features appear in this pattern is so I would like to claim that this is the beauty of the mathematics. It's not seriously. If you get the mathematical model and the design or algorithm, this model is. All right. This is another example. Dynamic sensor network, right? Depending on the range of the sensors, sensor will form their own network, right? And again, we need to solve the data association problem. So we need on data. And the other thing is the bottom here is the field robotics. This aim is to understand the environment of the robots. The robot is exploring some kind of territory, and then try to understand the map. That here it means that some static objects. And then if this robot knows static object, location of the static object means that it will obtain map. And at the same time, because I'm locating the objects, the static object, and relative distance between the object and myself, then I will also know the my locations. This is known as a SLAM problem, simultaneous localization and mapping problem importance. So all these examples can be solved by using the mathematical problems that I mentioned earlier in the Bayes and filter. And this slide just shows us that it is not still straightforward for multiple systems. This is because if you imagine that, okay, I have a single target tracker, single target, and you can do it by assigning single target tracker to individual targets. The thing is that when it comes to performance evaluation, it is not clear. You may think that, okay, I can measure this guy as a single error, this guy is single error, and so on. But mathematically, it is not correct because the number of objects is random. And this concatenation of the vector is not proper way to do it. By looking at this example. So there are two objects in the left-hand side, 0, 0, and 1, 1. This is true. And the estimated state, 0, 0, and 1, 1. There is no error, right? But if you match the 0, 0, and then 1, 1, then the error is not 0. Okay? So true object is defined by 4 by 1 vector 0, 0, 1, 1. I just concatenating to the coordinates. Then, but here the order matches. Change the order, the error is changing. So what we need to do is that we have to think about the computation of the arrangement of the vectors. But what I want to claim is that if this case, only the remedy is the computation. What true still exists, like 0, 0, and 1, 1, but the estimator only gives you one object, or the estimator only there's no how to measure the error. That's the problem. The previous slide, we only assume that the number of objects, at least they are matching together. But here, the number of objects matters, and when the number of objects matters, then there's no way to measure the error. Simple ways. So the motivation of the random finite set is the error metric in the estimated truth. When the number of objects estimated from the estimated change. What if there's a randomness in the number of objects? How to measure it? Starting from the definition of the error, mathematically, random finite set theory, in design, the proper state space model, then proper Bayesian what I want to do. So I already introduced you guys very shortly, like state space model and the Bayesian functions without giving you any equation. But when we need to think about other type of uncertainties, including number of objects, number of data, and so on, this is what we need to do. Okay, so random finite set concept is just collect all the elements as a set. So I want to call it as a meta set. Meta set is a mathematically a set that has elements, time-varying number of elements. So if we can mathematically properly the meta space, collection of the element, and also meta observation, the meta sensor, mathematically, then we can design the base state space model and base model. So again, I want to talk about the general ability. If you design your algorithm with a data-driven approach, you never do this. It's like a bottom up. But what I'm saying today is a top down. We always have a mathematical model that describes everything, and then we going down to try argument based on So again, I'm just repeating the propagation of two densities, H density, state density for multi-object states. But the problem here is that because of the number of elements is changing, so the H integration is not straightforward. So if you want to obtain the proper calculation of the integral of the number of estimates, that's why we need to introduce particular type of tool for integration so that we can go forward to design the model differently. Yeah, I'm not going to further giving you more information. This is the very simple code to realize random finite sets. The set number of points is random, and then points have no ordering, and they are random. And it is known in some other literatures, like in mathematics, the point process, random point pattern. So mathematicians are very interested in this point process or random point pattern to analyze some patterns, data patterns. For example, like in Scandinavian countries, they have lots of trees. They want to understand the distribution of the trees by using this kind of point pattern. Right? They want to analyze how they are distributed, when trees are distributed, and also they want to also understand population of trees. Simple method type here is sample first the number of elements, and then based on that samples number of elements, you can run the for loop. Then for each element, each iteration, you sample the state. Very simple, right? But what you can see is that distribution of the data points is random. The number of points are also. So you may think that it's a bit of boring or simple, but no. We ourselves will start from the very general description of something mathematics and design real time world. I can just skip here. This is also very theoretical, so I'll just skip here. Okay. Now, I want to briefly mention how the objects evolve in time and also senses as well by considering some concepts like the motion. Obviously, 2D object will change its location in time. That's the motion. And that's if the object is out of scope of tensor, we call it as a path. Or if if you think about the live cell could die in the subject because of some phenomena, and also it could divide into multiple cells, or there could be cell born, so on. So that's just the death of the object in the spawn, and the spawn is, as I said, mathematical model of cell division, for example. If you can mathematically model spawning, it means that you can describe cell division phenomena in biomedical. Creation is a form target. Target could appear from any direction, or in biomedical application, the cell could be born from single cell. Then we collect all of these, some kind of density as one, and then we call it as a multi-object transit density. So if you compare this multi-object density with a single transit density, we are not only describing motion, we are describing function. What about the measurement model? The measurement model, we just observe the target. They exist. There's no the data loss. It means exactly right. And there could be data loss, which is called as a misdetection. And also there's false alarm. Means that if the sensor is very high resolution, you could get the multiple measurements on the sensor. Or false alarm from non-targets. Okay? So I'll just briefly talk about this example of the class. If you look at the C wave, right, using airborne radar, then what you get is you send the transmit signal, you observe the reflected signal from the C space. The thing is, what is the difference between the sea environment and the aerospace is that in sea environment, because there's a texture in the sea wave, you could have very strong return from the sea surface, not from the ship. That is the type of the cloud. And then these return from the sea wave is very strong, but the location of the location of the return is random. The sea wave is fluctuating with random. So, if you have two models, multi-object density, multi-object motion, and then multi-object IQ model, you again can design the multi-object base group. Set is the conceptual solution, prediction, and the data optimization. And then in the table bottom here is we're trying to compare the single object case and the state of the system. In case of single object, it's random vector. In the case of multi object, it is not a vector form anymore, it's a random set. In single the case, we have a Bayesian filter, motor case, we also have a base motor. But as I said, the integration is still. Okay. If you remember the very basic policy theory, and if you integrate your PDF all over the space, what you get is one. Right? But in the case of motor density, it's not. So if you take integration on all space, in the case of motor density, and what you get is the expected number of objects. This is the main difference. This is the main trick of motor density. Then, in the classical PDF, integration over all space, you will get one. But in the physical density, integrate over all space, what you get is an expected number of. This is another description of the concept. So, okay, you can understand that infinitesimal density, modular density means that it's intensity information of the number of objects. That's why if you integrate over all space, what you get is the number of objects. So that conceptual solution has been investigated for 2 decades. And researchers out there try to develop approximation of the conceptual solution. But this one is the first example. And what we can simply case can summarize and approximate that motor density, conceptual density using first order moment, right? Which is analogically mean. And also the construction of the first moment is not good enough. So you can consider approximation of the another density, which is called cardinality density. And your cardinality is a special terminology in the set theory. If you remember that the set has a number of elements, the number of elements means cardinality, right? So we call it the cardinality density. So if you propagate 2 types of density, cardinality density and then first moment of the density, then you can have a full information. Estimation of the state and the number of objects. And so on. And this is another way to approximate the density. And then the first thing that denoted by R is the existing probability. The difference between the cardinality density and this one is that the cardinality density only looking at the number in the form of density, but here the existing density means that if you have a specific object, we want to describe whether that specific single object exists with a certain probability or not. There's another way to do it. And the other thing I want to mention here is that if you are familiar with the target tracking or detection, what you do is after getting the sensor scanning data, you apply thresholding, and what you get is a sparse set of measurements, point measurements, right? But when the the data from the object is not strong enough, the thresholding will give you few of measurements, or even there could be a significant detection loss. And what you can do is that you directly use image itself and scan image itself and then put that into the filter. But Bayesian filter can even accommodate the whole data. It's very general. But the other detail, you can see the reference. All right. So from this slide, I'm going to show you a bit of a short demo and conceptually how this conceptual type of simulated data applications. Scan the left-hand side, the sonar scan, okay? So, or radar scan. So, try to scan using edges and then radial distance. And you can see that the bright pixels, collection of bright pixels represents the return from the objects. But as you can see, there are many noises, high level of noises, or even false alarm and so on. In the bottom, window density, reconstructed density. Try to reduce after reducing some level of uncertainty. Okay? So if you obtain the density, you have some kind of expected information using Bayesian and the mathematical model derivation. And the other graph right inside is analysis information, which means that the time varying number of objects. In time, the filter gives you not only the spatial density in the middle, also the estimate of the number of time in the form of cognitive. And this is just a snapshot of the project funded by Lockheed Martin. And we tested the limit of the algorithm, how many number of objects we can accommodate. So in this case, we can deal with billions using. But of course, there are some limitations like target motion needs to be relatively simple. If density is growing, the complexity of models should be relatively simple. Otherwise, the algorithm is correct. And this one is, as I said before, this is another example, which is called simultaneous localization and mapping in robotics. As I said, the objective is jointly estimate the robot pose, the sample location, and also the length. I will skip, but the thing is, it can also formulate the bias in Bayesian concept. Yeah. So if we implement the Bayesian filtering algorithm that display the results, this is the case of SLAG model. What you have is that expected map. Expected map means the peak always gives you the static object that exists map. Not only location of the map, also uncertainty of uncertainty. But this has been done by the research group in Singapore. And they tested the algorithm for maritime situation using radar. And okay, so they tested the algorithm, implemented algorithm. As you can see here, is that the filter, the bottom shows us a relatively accurate results. You see the estimated location of the steady object, the ground truth, they are matched compared to the existing previous algorithm research first case. Okay, and also as I said, the Bayesian solution is general enough so that we can even integrate the homogeneous data. This is another example of the fusion of vertical ETL. So computer vision is all about vision sensing. Also, sometimes vision sensing is not good enough in the case of visual vision. And there needs to be another type of data. Otherwise, visual vision in the long term not be resolved. I'm not sure that whether it's it's a very simple example, but it's a proof of concept. So again, the state space model and Bayesian filtering, these concepts are very general. So likelihood model of the sound and the likelihood model of the vision detector they can be described in PDF. They can be integrated by the concept of Bayesian solution. All right, this is another example of the visual solution. All right, this is relatively recent result. So if you look at the image, this is a scan image in the Everglades, in a high elevation, and we want to look at this very small object, the seasons, which is denoted by using scale. But if we notice that square, it's really difficult to recognize the small. As I said, June, the return from the target is very key into the noise rating. So this example cannot be solved by the heuristic one. The Bayesian solution can accommodate that because we have motion model of the object, how they will move in time, and also we have the sensor model so that we can very small number, small number. So I have two reactions when I show this demo. First, I think it's gross gamma because the data and the reference size doesn't have any at all. You can't recognize anything meaningful information from the reference size. But the estimator is giving you there are multiple number of objects and unchanged indication. This is possible because, as I said before, we have motion model, how they will move in time. We have the data model. So in this particular case, the classical data thresholding-based detector doesn't work. Vision is outdated. So I will show you them. Okay? So this is the test data case of crowded scene. There's a limitation, of course, because detection doesn't give you the perfect data. And that's why on the right hand side, we are not only considering the square detector, we also want to try to extract some information from the person. There's the circles and then the small cross, the extracted features from the features. So we can accommodate some data loss. I mean, significant data loss from the vision. And another example, on the left-hand side, one is a point detection that describes the dislocation of the multiple cells. What's different here is that, as I said, there will be cell division, cell data, cell deaths in the cell bone. Not the case in the previous application, right? Even general solution can somehow accommodate those challenges, like cell division and then cell bone and cell disease. Good. It is not interesting anymore, but the Bayesian multi-object system solution can be also applied for autonomous speed. So this solution has been implemented in the Mercedes, and they tested the implemented algorithm. But nowadays, this algorithm is well advanced and deployed in your system. Okay, the last one I would mention here is that previous examples are tracking application. What we can do, sensor control, sensor management. So it means that there are some objects out there, then there's some vehicle, and I want to control this vehicle to increase the observability of it. So here it means that there are multiple objects, like blue ones. Blue ones represent multiple objects, and they are moving arbitrarily. And then starting from the 0, starting point of the sensor, I want to move the sensor towards the cloud of objects, and I want to increase the quality of the sensor data. This is active. I'm not just trusting the data from the sensor, I also want to move myself to increase the quality of the data. But the thing is, we can design heuristic algorithms, but using Bayesian solution, we can somehow optimize some cost based on the processed data from the Bayesian filtering, and then we can increase the data quality in sensor management. This is the set the sensor actually starts its location from the 0. It will move for the multiple objects. It's not arbitrary, it's control. After getting the statistical information, we need to design some kind of information based on divergence, mathematical divergence. And we want to minimize that mathematically defined divergence based on multiplicity. Then we can design this kind of sensor management, sensor control algorithms. So briefly speaking, when you construct multiple density, you will know number of objects and the location of the object, right? If the sensor is straight in the center like a 0 and 0, quality of that density, approximate density will be really correct. But if you move your sensor toward the number of objects, you could have higher quality of the data and higher quality of estimation of the multiple objects. Okay. So this is another example. So if you look at how the sensor is moving compared to this previous example, sensor is moving a little bit of zigzag motion, right? This is because of the this particular divergence cost. So if you can think of more efficient divergence cost, then you will move straight away towards the multiple objects. I want you guys to give a chance later try to think about what I've introduced today to transport vision systems and products. Okay. This is the end of my talk. Because I've been talking about very general concept, how to describe multi-object system. It could be applied to many applications. That is what I want to deliver. Thank you very much.
Thank you, Dr. Kim. If you guys have any questions around this presentation, please do so. Is anyone doing any image processing research? No one is doing any image processing. Really? Seriously? Guys, no one's doing that? But what about the data analytics? The supervisors, I think you should have told. What are you guys studying there? I'm new here, I don't know why you guys are studying, but you should tell us.
I don't know. Nowadays, if you're dealing with some data and you guys are familiar with at least certain there are many machine learning algorithms out there based on these statistics.
Jung, you formulate all the equations, you say you're doing it from top to down the way. But these, I think the most students and the gentlemen, these days they're pretty much doing a data-driven approach. So just plug in all the data into some model.
Yeah.
Okay, then predict outcomes out of it. Even for this, deep learning stuff such as neural networks, so you don't really know what's really going on there. But when it comes to accuracy rate, for example, so but I keep thinking about the YOLO system, okay, compared to yours.
Yeah.
The people like YOLO system very much because it does actually have very, very fast and I also the accuracy rate is there too.
Yeah.
What do you think about that? What do you think about why we keep doing this equation formulations rather than we keep collecting data and produce much faster and better outcomes?
Yeah, well, back then when I was PhD student, at the time still deep learning algorithm was not trained on this. And I just observed the rise of the deep learning algorithms in 10 years, but still we criticize that we want to understand what's going on in that black box by using some tools. I'm not talking about what statistics or Bayesian that thing, but at least we need to learn to understand how the black boxes work, so that at least by considering that concept. And also, of course, I know that the modeling is difficult, and if the data operation works really, really well, we also do that. But what I'm claiming is that there needs to be some variation. That maybe the modeling can save some advantage of the data-driven approach, or data-driven approach. This part can be done by using that.
From the students, anyone's doing the artificial intelligence, okay? What are you guys doing?
The thing is that you're familiar with church of the network. And back in like the 90s, and there was some attempts to how the neural network is working by using Bayesian neural network.
Yeah.
And to try to follow the uncertainty of the connection of this field.
I think nowadays we a lot talk about the artificial intelligence, right? Neural networks, of course, in part of that. You also start talking about because these guys all criticized the black boxes there. So now the people started talking about explanatory artificial intelligence. If that becomes good, if that becomes proven, do you still believe your work is valid?
Well, I must say that maybe it would not be valid anymore. You can use successful to find the technology. But there are other applications that cannot be done by the deep neural time series investigation. So I feel like this Bayesian filter has been some sort of main research area back in 10 years ago, 20 years ago in community conferences.
Yeah.
So now it's not the main.
Yeah.
So and then same things will change. Nowadays my topic and our topic move to statistics all around.
Yeah.
So I want to say some points to students, you just forget about everything that I've delivered today. But a lesson you need to take is that you need to think about what you're doing, not just dump your data. Uh, you need to know what you're doing. Doesn't matter whether it's a don't work properly, but you need to know what you're doing.
I totally agree with you.
Yeah, otherwise, this is not very easy.
Yeah.
Yes, interrelated. I understand that, not statistically independent. That's, somehow related to the, cell division or cell interaction, thing. And then investigators and researchers out there try to advance that simple model for homemade production. No, what about social force model? Like that. Especially try to photo. Describe it. Right. Here, does it have to be physical? Transportation. Yes. Hearing. Yes, ma'am. Yes, I didn't mention about the prediction here, the smoothing. And when it filtering, filtering means that time critical for this. So it's when you want just like a steady time, current time, right? If you construct the whole data distribution, what you can do is that you can predict even and also smoothing. Smoothing means that what is all the data, and you want to estimate certain part of it, and you will have a more accurate estimate compared to the real time. Yeah. Yeah. Frankly speaking, it seems like the prediction is look, you're using the intellectual based model. Prediction is really, really good. But again, you don't know the evidence found or the level of that decision. That's the main thing.
And Tuyong studied in Korea for 10 years and studied in Australia for 10 years. Okay. What's different between these two in terms of doing the research?
I spent my time 10 years as a graduate student, not as a professor.
Yeah.
So I can't compare it. But what I can say is that the students here is way more smarter than the dependents.
Yeah. Okay.
So
a student here way quieter than Australian student.
That's the question, right? So I want to say that you guys are smart, so you can just ask any question. Australians, a Western culture, they just ask question, really, really stupid question. Sometimes I feel like I waste my time, but they are doing that, and by doing that, sometimes you get something. You guys can make good balance, like not asking any question without reading book, right? Guys at least read some books and try to understand what you're doing and study harder, but ask questions into your books and make them study. Oh no.
you think there is any opportunities for you to recruit postdocs in near future?
I'm always open to postdoc, but my application nowadays is basically defense research. On the radar and sonar and in maritime defense area. So if you guys are, but defense area application compared to the vision and machine learning is very secure and very confidential and exclusive. It means that if you an expert in this area, you have more trust. There are pros and cons, of course. So if you are interested in topics or research,
Can you publish papers through the defense project?
yeah, we can do that.
Okay.
Because we start from simulated data that we can publish. And we move to the next level, and we deal with the classified data. Then results from the classified data are also being published.
Yeah.
But we publish this.
Okay.
Yeah. Classified data, dealing with classified data way more very population.
Students are interested in the postdoc in Melbourne, Australia. That's the one.
And also it's a good experience for you guys to be outside country. And experiences level. Who knows? You just leave what you leave in Melbourne or just speak.
Yeah. Guys, have any more questions? Further questions? And please, yes, please. Go ahead.
I just said it's different. But you how can they consider about it?
I mean, sure. When the objects are yes. I didn't mention about the interaction, I mentioned about the pollution, and then the other topics, related topics. That I only want to spend this time. Because it's very easy. So you can borrow anything, you can describe phenomena using mathematics. And for pollution, it's not so yet. So the computer vision and the other application really headache in real system. Now, deployed algorithms out there in general work, Tesla or some other startups, they still develop some algorithms. So, very difficult problem.
That seems to be a good topic, though. Yeah, this study.
Oh, good.
Yeah. I think time is almost up. So thank you for coming, guys. And we're gonna make this kind of seminar more often. Okay, so please feel free to come attend this kind of seminar and always think about some questions around. Okay, all right. Thank you very much for
Thank you very much.